Hi, I'm Hermine Maas, and I'm going to walk through an OpenMX script that was used in the practical on day 3 of the virtual Boulder workshop in 2022. We'll comment on the practical day 3_r.r script, which is the companion script to the one used in the practical that is in the faculty drive under HMAS 2022 day 3. The script starts with some comments that provide a bit of guidance to what is to follow. Then we open the OpenMX library as well as the psych library, and we'll use the NP-Sol optimizer as indicated in the MX option here. We will source the myfunctions.r script, which has a number of functions that make scripting a little easier. We then load the twin dataset that is associated or part of the OpenMX package. And here we show the codes that are used for the different zygosities by sex combinations. In the first part of this practical on sex limitation, we will focus on the younger sample of adult twins in this data set. These are the zygosity codes 1 through 5. So we first subset those from the main data set and calculate their correlations in R, just as a way to get a sense of what the data look like before we get started with OpenMX. We also plot them here. And as you can see, the observed correlations are considerably larger for the MZ groups, with the female MZ group RMZF equal to 0.78 and the male one to 0.77. These are the twin correlations that we will compare with the DZ twin correlations. Those are in the 0.3 range, with the opposite sex correlation, RDZO, a little bit less than the same sex correlations for DZs 0.3 and 0.32. So these correlations give us some indication of which genetic model is more likely going to fit the data better. And as the DZ correlation is less than half the MZ correlation for both the females and the males, we expect that an ADE model will fit these data best. Furthermore, there doesn't appear to be very obvious quantitative sex differences, given the twin correlations are rather similar between males and females. However, the DZ opposite sex twin correlation is lower than the same-sex twin correlations, which could indicate qualitative sex differences or different effects of genes or environmental factors in males and females. That was just a way of introduction. Next, we're going to walk through a number of scripts, and we start with a two-group script, similar to the ones you've seen in the practicals on day 1 and day 2, where we just distinguish between an MZ and a DZ twin group. This script is exactly the same, except that I have stripped it from the comments to just make it as concise as possible, because this was in part a repeat of earlier practicals. But I'll walk through each of the comments as we run this script to refresh everyone's memory. So first of all, here, of course, when we were just to open this script as a separate script, and you can find various versions of the scripts that are fully commented on the OpenMX script website. So we open the dataset and typically have a quick look at the descriptives using the describe function in the psych package. You see that this is a reasonably large data set of twins, where BMI 1 is the observed measure of body mass index in the first member of the twin pair, and BMI 2 in the second member of the twin pair, where the assignment to twin 1 and twin 2 has been randomized. We also look at the age variable in this sample, and basically we divide it by 100 to make optimization a bit more smoothly. And because age is going to be used as a covariate, as we know that BMI changes as a function of age, we therefore will include it as a definition variable and thus need to use a sample where there are no missing values for age, because there would not be a predicted covariance for that particular pair if the age is missing. Here, we will first apply this two-group script to the male twins, whose zygosity codes are 2 and 4 for MZs and DZs respectively. So we subset them here again. And now we go first into the saturated script that will fit separate means, variances, and covariances, as well as include age as a covariate. And the likelihood of this model will provide the baseline likelihood with which we compare the likelihood of the genetic models that will fit later. This is still a univariate analysis, even though we have two members of a twin pairs that are observed. So we define NV as 1 and NTV as NV times 2, or in this case, 2. The variables, the dependent variables of our analysis are BMI 1 and BMI 2, and age is a covariate. As I indicated, we will use age as a definition variable, and that's done by changing the label of this MX matrix to something that starts with data dot and then the name of the variable that OpenMX will look for in the data set to use it in the expectations. Part B is the MX matrix that will hold the free parameter for the regression coefficient on age. And then we have mean MZ, mean DZ, the MX matrices specified to hold the intercepts for MZs and DZs. These are 1x2 matrices that are freely estimated with separate labels for twin 1 and twin 2, as well as for MZs and DZs. As we also want to include age as a covariate, the expected mean for MZs and DZs is the intercept plus the regression on age, which is specified here with the C-bind matrix algebra statement. Next, we specify the expected covariances, and in this case, that's just a symmetric matrix with the variances on the diagonal and the covariances on the off diagonal. We give them start values as well as lower bounds, such as the variances in this case are to be estimated to be positive. Then we put the observed data objects into an MX data object and declare that we are using raw data. And the expectation indicates what the expected matrices are for the means as well as the covariances, and matches them to the dependent variables identified by the selvars object. We then use include the fit function to be used, and in this case that is maximum likelihood, so MX fit function ML for maximum likelihood. And then we build the models separately for MZs and DZs with all the various objects in there, the definition variable for age, the regression on age, the expected means, expected covariances, the data, the expectation for to connect the model with the data, as well as the fit function. And because we want to evaluate these two groups simultaneously, we also specify the MX multifunction, MX fit function multi-group option with the names of these two models as its arguments. Next, we specify for which elements we might want to estimate confidence intervals. And we do this for both elements of the covariance matrices as of the means. And then we build our overall model called model SAT. That includes as its arguments these models we've defined before, model MZ, model DZ, as well as the multi-statement to indicate that we want to estimate them simultaneously, and include also the potential confidence intervals statements here. This model also gets a name within as part of the arguments, and that will be used in the summary or in the MX compare later on. So now we're finally ready to run this saturated model. And for now, we're not estimating confidence intervals, so we set them to false. And you see here that it ran the model with 11 parameters. So we have the two means, 4 variances. Oh, actually 4 means, 4 variances, 2 covariances, and the regression on age. We then use one of the functions from myfunctions.r to list all the goodness of fit statistics on one line. And we also have a function that quickly summarizes the estimates of all the free parameters. We call this fit ests, and this lists all the free parameters as a row vector rather than as a table with a lot of additional information. Of course, once we fitted the full saturated model, we also use this to test a variety of assumptions, such as equality of means across twin order, so between twin 1 and twin 2, as well as equality of variances across twin order and equality of means and variances across zygosity. So that's done in these 3 submodels, fit EMO, fit EMVO, and fit EMVZ. So that is means for twin order, means and variances for twin order, and means and variances across zygosity. And then we can use the MX compare to provide a quick summary of this set of assumption tests. And we can tell here that given we have a non-significant chi-square or non-significant p-value for model 2 and 3, the first 2 submodels, indicating that there is no significant difference between the means of twin 1 and twin 2 or the variances of twin 1 and twin 2. However, for the males here, we do see a significant p-value when we test equality of means and variances across zygosity, indicating that we might have an issue to deal with prior to our further model fitting. This could be due to some outliers that have a large effect on the goodness of fit. For now, we're going to leave it at that, and because the focus of our practical is on sex differences. And so instead, what we'll do is assume that that the assumptions were okay, and move on with fitting either the ACE or the ADE model. In this case, for didactic purposes, even though we already have an idea of which of the 2 models is going to fit best, I'm actually going to fit both of them so that you see what differences you can observe when you do so. So let's walk quickly through the code for the ACE model. And given we've established that we can equate the means, we will just use 1 mean instead of 4 means. But we will still adjust that mean for the effects of age. So we have age as a covariate. And now, instead of estimating the variances directly, we are going to estimate 3 variance components that we can derive from reparameterizing this model as a genetic model. So we have COF A, COF C, and COF E to hold the free parameters for the additive genetic, shared environmental, and unique environmental variances. We then use some algebras to calculate the predicted total variance in COF P and the predicted MZ and DZ covariances as VA plus VC for the MZs and a half VA plus VC for the DZ group. We then need to put together the predicted covariance matrices, and these are 2x2 matrices with the variances on the diagonal and the covariances on the off diagonal. So we do this with R binds and C binds. The expected or the expectation normal here will of course refer to the right objects for the expected covariance matrices as well as the expected mean, but note that the expected mean is now the same across these two groups. And then we of course have to indicate that we're still using maximum likelihood. And as some of the objects will be used in both the MZ and the DZ group, we put them first in a list that we call pars, short for parameters. And we have a separate one, diffs, for the definition variables, because those are only included in the models that actually have the data and not in the overall model. So the models contain all the objects that are necessary. And then we have again the MX fit function multi-group. And then we also include an algebra that will quickly give us not only the unstandardized, but also the standardized variance components by dividing each of the variance components by the total variance in the matrix V. In this case, we likely want to get the confidence intervals around these variance components, and we choose here to do that for the unstandardized ones. And then we put everything together again in this case, model ACE, which we will fit with the MX run statement. And of course, we can still use, oh, it looks like I missed running the parse line, so I'll go and do all that again. Oh, there is still a problem. Let's try the whole thing. There we go. It's a bit tricky sometimes to do this line by line because I might forget to actually run a specific line. Now it did run fine. And you can see here from the MX compare where the ACE model is compared with the saturated model, that again, we get a significant chi-square, which is of course to be expected given there were some issues potentially with the assumption about equality of means and variances across zygosity. We then get the estimate. So in this case, we have the mean or the intercept, the regression on age, and then the three variance components. And we also have estimated their likelihood-based confidence intervals here. So it appears that from this model, it appears that the additive genetic component is the largest component, and we get a negative estimate for the shared environmental variance as expected, given that the pattern of correlations was not consistent with an ACE model, but instead with an ADE model. So we're going to skip fitting the submodels here, but move to the ADE model. And you'll see that this part of the script looks very similar to the ACE model, except now, of course, that we call the COF-D matrix where we store the dominance genetic component. We adjust the covariance for DZs to a half VA plus a quarter VD. And then we make sure that we replace all the C's with a D. And basically that's all we need to do to now fit the ADE model instead. You can scroll back and note that these two models fit exactly the same as far as their likelihood is concerned, because they have the same number of parameters, and you can either parameterize this model, this direct symmetric estimation approach model, as an ACE and an ADE model. You'll get the same fit, but of course, it makes more sense for the interpretation to use the ADE model, where we have a positive estimate of both VA, VD, and VE, rather than looking at the results of the ACE model in this case. We can go a step further and then test the significance of the parameters of our ADE model. So here we will test the significance of dominance by fitting an AE model. And then, of course, we can also fit an E model that basically tests whether there is significant familial resemblance as we drop both A and D. And we don't fit a DE model typically because it's really not biologically plausible to have dominance without additive genetic variance. So let's compare these models. And as you might expect, we have significant p-values for both of these models, indicating that both the dominance and the additive genetic component are significant for the data on males. And here, this last statement is another way to get the results for the unstandardized parameter estimates, but also the standardized parameter estimates. So this was that algebra that generated just a list of the variance components and the standardized variance components. And then we repeat this for the three models so that we get all the results at once. Okay, so it appears from this analysis that the broad heritability is about 17%. And I probably messed this up, so I shouldn't talk about broad and narrow heritability. One is just the additive genetic variance divided by the total variance, and one is the sum of the additive and the dominance genetic variance divided by the sum of the variance components. So the total heritability is in the order of 77%, with the remainder of the variance accounted for by unique environmental factors. Okay, so that was a quick run through of the two-group model for the males, and we can repeat this for the females simply by going back to the top, changing the zygosity codes from 2 and 4 to 1 and 3 for the young female twins in this sample. And then we'll start from here again, run through the saturated model, test the model assumptions. And in this case, for the females, you see that all three assumptions are valid because we have three non-significant p-values. Again, we can have a quick look at the ACE model, but as you might expect, we also see a negative estimate for the VC variance here because the correlation for the females were also more consistent with the dominance model. So we will fit an ADE model and see whether both A and D are significant, and they appear to be, as indicated by these significant p-values. And we now have also the estimates for females, where you see that the total variance again is in the same order of magnitude, in the high 70% range, with about 22% accounted for by the unique environment. However, the relative magnitude of the additive and the dominance component seems to be reversed in males versus females. course, the big question for this practical was whether there are sex differences in the magnitude of these variance components between males and females. Now we can, of course, eyeball these results and say, oh, I think these estimates are different from one another, or oh, maybe I don't think they are that different from one another. The E component looks spot on, so maybe there isn't a significant difference. But that's typically not the way we do things in statistics. And so to be able to test whether we can, these variance components are significantly different between these two groups of males and females, what we're going to do is have to combine the two sets of analyses in one analysis so that it allows us also to put some constraints on some of these parameters, such that the male parameters are equal to the female parameters, and see if that model fits significantly worse compared to a model that allows these parameters to be freely estimated, as we have done here separately for males and females. So how do we do that? We start with a four-group analysis. And so this script that you see here does have all the comments included, and is slightly modified from one set for CA. One stands for one phenotype, SAT for saturated model, four for four group, C for continuous, and A for the fact that we have H as a covariate here. Instead, the main difference here is that we're now subsetting the twin data for the four same-sex groups. And we can, of course, just as a check, also look at the means and the covariances using basic R code. And then we're setting some start values that we'll be using in the later statements. So let's start and run the top part of this script. Okay, so you'll see that the means are actually reasonably similar across males and females. Of course, that's not the focus of our analysis here. We're going to focus on the variances and covariances. And maybe you can spot already here why we saw a difference in the means or variances for MZs for the males between the MZs and the DZs. As for the MZs, it looks like the variance is a little bit smaller. So now this script, I think, will start to look rather more familiar, except that we now have to double up a lot of the statements because we have matrices and algebras for both the males and the females in one script. We just have one definition variable still for age, but we allow the regression on age to be estimated separately for males and females in the top part. Then we now have four matrices for the means. This is the saturated four-group model. So all the means are first estimated to be different. And we then, of course, have four statements for the expected means where we also correct for the effects of age. We now have four expected covariance matrices. In this script, we also calculate the expected correlations by using the COF to core function. And then we have the data groups, the expectation normal statements, and then we have to build the models for each of the four groups here and define with the multi-statement that we're all going to evaluate them together. Again, we can estimate some confidence intervals if we're interested in those, and then pull all the four models together into an overall model that we still call model SAT. But note that the name here now indicates that this is the four-group script. Let's run that and look at the main output. We have 22 parameters. Remember, we had 11 in the two-group problem. And here we're basically just refitting the two-group problems as a four-group problem. And you can verify that by checking both the degrees of freedom and the likelihood of this model should be basically the sum of the degrees of freedom of the two prior models, saturated models that is, and the likelihoods of the saturated models separately for males and females. And the estimates of the parameters should be actually spot on to the ones we obtained in the two-group analyses before. Here, when we do the assumption testing for the four-group analyses, we added a couple of extra submodels here that test the significance of age as a covariate by dropping it from the model or by seeing whether we can equate it across males and females. And both of those tests are significant, as you'll see in a minute. And then we have the same assumption testing as we did in the two-group case, but now we add an additional test to see whether indeed there are differences in the means and the variances by sex, which of course will be our first indication that there might be sex differences in the variance components as well. So that's done in this last bit here. And to see whether or not that is significant, we'll compare it with the overall saturated model using the MX compare, which will have, first of all, the tests for the covariate, and you see both of those are highly significant. So we will keep the covariate in the model. And then we have the tests for the equality of means and variances by twin order. Those appear to be fine. And by zygosity here, again, we're picking up the significant chi-square, probably due to those males, the MZ male group that has slightly smaller variances than the other groups. We also pick up a highly significant effect of sex, both that is in an overall test of the equality of means and variances across sex. So that implies that we will also include a separate mean for the males and the females when we do the genetic analyses. And of course, we're focusing on the differences in the variances and also in the variance components that we will be estimating in ACE or ADE models. Now, given that we already know from the two-group models of the two-group analyses that the ADE model is more consistent with the pattern of correlations in these data, we will skip the ACE model here and move on directly to fitting the ADE model. Again, the script looks very similar to the two-group script, except of course here we do include the comments, and we also have basically almost every statement doubled up to account for the parameters in males separately from those in females. So first we set some start values, PA for the A and the C components, PE for the E component. We again have the same definition variable and regression coefficients for age. And we now, instead of estimating separate means for every observed mean, we now only have one mean for males and one for females. So we use the same label for twin 1 and twin 2's means, but we allow different labels for the male and the female means. And we then include the regression on age. When we define the ADE variance components, we now do this separately for females and males. So we add an F and an M to the end to indicate that we have separate free parameters because we use different labels for female and male groups. We then, of course, also have to extend the expected covariance matrices across the two sexes. So we now have 4 expected covariance statements for each of the 4 groups. Similarly, we have 4 data statements and 4 expectation normal statements. And then we pull it all together in 4 models. But here we made 2 lists, one for males and one for the female objects that are needed in the respective groups. And our multi-statement now, again, includes the 4 models that we will be evaluating together. Here, again, we create a little algebra so that we pre-calculate or basically just list the unstandardized estimates and pre-calculate the standardized estimates. We do that in this case so that we can also then potentially estimate the confidence intervals around the standardized estimates that we put in this matrix called US here. As you see here, this is the statement that indicates which parameters we want to estimate confidence intervals for. And right now it's set up to do that for the unstandardized female variance components and the unstandardized male variance components in elements 1 to 3 and 7 to 9 of this row vector. We then put everything together in the overall model. Note that we have all the objects in for the females and the males in pars, and then the actual models, the 4 models for MZs, DZs, males and females, the multi-object, and the matrix with the estimates and the CIs. Okay, we're ready to run this model. So we added a Q here in the name of this model because this is a model that allows for quantitative differences in the ADE components. So here we run the model and we now have 10 parameters. It's often a good idea to make sure that you know which 10 parameters you're going to be estimating, and double check that when we look at the statistics. So we have, again, used the fit GOFs to get the 1-line results of the goodness of fit statistics, and then the parameters with fit ests. Or if you use the fit ests CIS command, that not only lists the parameter estimates, but also their confidence intervals. If you look carefully at these numbers and remember what they were for the when we did the 2-group analysis, you may see that they are spot on, the ones for the 2-group analyses, because we have no constraints across the male and the female groups. So the key piece here is, of course, now to test whether or not these variance components are statistically significantly different from one another. And we do that by 3 simple OMX set parameter statements that allow us to say that we don't want to estimate separate estimates for males and females anymore, but instead of the VAF and the VAM elements, we now are estimating one element that we call VA, and the same for VD and VE. We estimate the same parameter for the male and the female groups by specifying these 3 statements. And thus this part of the script tests whether or not there are quantitative sex differences. You see in the MX compare that we compared this model to the previous one that had 10 parameters, and we now estimate 7 parameters because we've added 3 constraints. These are equality constraints, so we have gained 3 degrees of freedom. the chi-square likelihood ratio test is 12.8 for 3 degrees of freedom, which is highly significant. So what this tells us here is that we can't constrain the variance components to be the same in males and females. And so the separate estimates that we obtained in the two-group analyses stand, and even though we can list the constrained estimates, these actually don't provide a good representation of the observed data. So with this data set, even though the pattern of correlations looked very consistent across males and females, it appears that the variance decomposition actually suggests a different pattern of results in the two groups. Now, so far, we've only used the same-sex twin pairs. You may recall from the theory lecture that we have an additional statistic in the opposite-sex twin pairs that allows us to estimate an additional parameter that will be allow us to evaluate whether, in addition to the quantitative sex differences, there might also be qualitative sex differences. And the difference here is that so far we focused on the magnitude of the variance components and tested whether those can be equated. The qualitative sex differences tests whether or not there might be a different set of genes in males versus females, or a different set of shared environmental effects if those were important contributions in the model. In this case, technically, one could test whether there are a different set of genetic factors with a dominance genetic effect. So we're going to focus on testing whether or not there are different sets of genes involved potentially in males and females. And if that's the case, then we would expect the DZ opposite sex twin pair correlation to be significantly less than the same sex DZ correlation. And so to do this, we take a model that looks very similar to the 4-group model, but we add the 5th group for the opposite sex twins. And to do so, especially in the context here of estimating the direct variances, it actually involves a little bit of extra algebra, because remember that we want to allow the variances to go negative. But if they do so, and if we were to then multiply the male and the female, the square root of the variance components of males and females, that would force those variance components to be positive. And so we need to invoke a bit of extra algebra to still allow the variances to go potentially negative and to avoid the issues of biased comparisons of models that we get when we constrain the variances to be positive. Okay, so let's start with this part of the script, and you'll see, again, you'll find a separate code or a separate script that is called 1ADE5 VCAM, and the M stands here for the way we estimate this additional parameter is by adding in an extra set of genetic factors in males, which is one way of doing that. The alternative way is by directly estimating the genetic correlation across sex, but that correlation can also be calculated, as you'll see in this script, from both the common set of genes in males and the male-specific set of genes. So the first part of the script you'll see is very similar to what we've seen in the 4-group model, except that we now also, of course, have to read in the DZO data. And what's critical about this too is that the DZOs are organized in such a way that twin 1 is always one sex and twin 2 the other sex, unless you make two groups where you have a different order in the two groups. So in this case, we have the data organized such as twin 1 is always female and twin 2 is always the male twin. Then we prepared a model where the statements with respect to the definition variables and the regressions on age have not changed. But when we get to the expected means, you'll see that obviously for the same sex groups, they have not changed. But for the opposite sex group now, we need to make sure that we have the appropriate mean constrained to the mean of the respective same-sex groups. So in this case, the mean for twin 1 is the same label as the female expected mean, and the mean for twin 2 is the same as the expected male mean, because that is the male member of the opposite sex twin pair. And that's also reflected in the regression on age, because that was also sex specific. We then, again, as before, have the 6 covariance statements for ADE in females and ADE in males. But now we have 2 extra parameters, of which we can only estimate 1. And so in this case, we're going to freely estimate VAMS. VAMS is this male-specific set of genetic factors that, if this is significantly different from 0, will lead to some evidence for qualitative sex differences. Next, you'll see the bit of code that is necessary to still allow the variances to be estimated to be negative. We don't expect that to be the case in this example here, because we're only fitting the ADE model, and we know from the separate analyses that the dominance component was estimated positively because of the pattern of correlations. But what you see here as well in the last 2 lines is this is the way we calculate the genetic correlation across sex based on the female additive genetic variance component, the male additive genetic variance component, and then the male specific additive genetic variance component. So we multiply the female by the male component and divide by the square root of the female times the male component, where the male component is the sum of the common and the male specific components. Then, of course, we have to put together the expected covariance matrices for MZs and DZs based on these A, C, and D, A, D, and E parameters that we declared before. And so we know how to do this for the same sex groups, but note that for the males, we now have VA plus VD for the male components that are common, and then VAMS and VDMS for the male specific components. And similarly for the DZs, we have both a common set of genes as well as the male specific set of genes that need to be included for the expected covariance in male twins. Our DZO twins, we already pre-calculated in algebra VAOS and VDOS for opposite sex twins, so we use that here in the COV DZO statement. And then we bring the variances and the covariances together for the expected covariance statements. And everything else is starting to look rather similar, but instead of 4, we have 5 data groups, 5 expectations, and 5 models. Note that for the DZO model, we include both the parameters that we need for the males as well for the females. But other than that, it looks rather similar to what we've seen before. Oh, I did it a few times. Too bad. Okay, now we again create our little US matrix that has all the unstandardized and the standardized variance components. But in this case, I've also added the RG and RD parameters. In this case, of course, we only estimate RG because we can't estimate them both at once. But we get that at the same time as these other estimates of the variance components. And we can also ask for confidence intervals around each of these unstandardized parameters and the genetic correlations across sex. Now our model ADE RA for the genetic, we could have, sometimes it's called RG, I called it here RA for the genetic correlation across sex. So this model will include both quantitative sex differences, because we still allow the AFs to be different from the AMs and so on. And we estimate freely, in this case, male-specific additive genetic factors, which allows us to calculate the genetic correlation across sex. And so we pull all that together, all 5 models, into an overall model that we then run and can look at the output. We're estimating 11 parameters here. So that's the mean for males and females, the regression on age for males and females, VA, VD, VE for females, and for males, plus this additional VAMS now for males that allows us to estimate the genetic correlation across sex. Okay. Now that we've done all that, of course, we want to know whether that genetic correlation across sex is significantly different from 1. So if it is 1, it means that the same factors contribute, the same additive genetic factors contribute in males and females. If it's estimated to be significantly different from 1, it suggests that there might be a set of genes in males that is different from those in females, but it gives us an indication of the degree to which the genetic factors are the same in the 2 sexes. So that's what we do here in the next set of submodels. So we started with a full model, so to speak, a model that included both quantitative and qualitative sex differences. So in the first instance, what we do in this case is actually, instead of the RA parameter being estimated, to estimate the RD parameter, or basically instead of estimating the male-specific additive genetic factors, we fix those to 0 and estimate instead the dominance-specific factors. And thus we can derive from that the dominance correlation instead of the additive genetic correlation. To test whether or not these qualitative sex differences are actually significant, we will look at the correlations in just a minute. We will then set that correlation to 0, set that correlation to 1, or if we are specifying the model with male-specific sets of genes, we set that male-specific set of genes to 0 to drop it from the model and see whether it fits significantly worse. You'll note here that I include a statement for the unique environmental component. Basically, what I do here is just make sure that they get started at a reasonable start value. So I start them back at the original start value. This is just to make it a little bit easier for optimization to to converge. Now, dependent on the result of this test for qualitative sex differences, we will or will not run quantitative sex differences. And I'll explain why. If there are qualitative sex differences, it may not make sense to test whether the additive genetic component, if that's the qualitative sex differences that we're estimating, if those can be equated, because if not all the same genes that contribute to the trait in males also contribute to the trait in females, then it would be rather unlikely for the amount of variance that each of these different set of genes is explaining in the phenotype for that to be exactly the same. So typically, if we find significant qualitative differences, we would not test the quantitative differences. In this case, I'm running through each of the models because we combine them here in this MX compare that we're going to be evaluating. So the first model was the model with that estimated RA, or the genetic correlation of additive genetic factors across sex. And the second one was estimating the dominance correlation. And you see that basically these two models both fit the same. So the main question now is whether we can drop that parameter from the model to test whether the genetic correlation is equal to 1. And it turns out that that likelihood ratio test has a value of 2.3 for 1 degree of freedom, so it's not significant. We could look a little bit further down here. If we estimated the model with RG, you see that RG was estimated at 0.88, and with this sample size, that is not significantly different from 1. And so we conclude here that there are no significant qualitative sex differences. As I said, normally we would then not continue on with the test for quantitative sex differences. And so this is maybe an unusual example where the qualitative sex differences, oh no, it's not an unusual example. So it's saying, well, there are no qualitative sex differences, but there appear to be quantitative sex differences because this second test, as we saw before, is highly significant. And again, the significance is maybe driven in this case primarily by the fact that in females, it appears that the additive genetic component is larger than the dominance genetic component, whilst in the males, it is the reverse, with minor differences in the unique environmental component. But if you look more carefully and add up the 3 variance components, you note that the total variance is higher in females versus males. And that is the case not only for the sum of the additive and the dominance genetic component, but also for the unique environmental component. So based on these analyses and this sex limitation model that we fitted to these data on BMI in male and female twins, both same-sex and opposite-sex twins, is that there are no qualitative sex differences, but there are quantitative sex differences in the 3 sources of variance that contribute to BMI based on these data: additive genetic factors, dominance genetic factors, and unique environmental factors. That is the end of the sex limitation practical. We'll record a separate video on the G by E practical. Thank you very much.